this lesson on torque, we thought it'd be a good idea to begin the online portion with a review of rotation so far. So let's begin with a comparison of linear and angular motion. Your study of kinematics began with a discussion of how far and how fast, which led to the introduction and definition of a few key concepts: distance, speed, and acceleration. Each have their equivalent value in a rotating system: theta, omega, and alpha. These were combined to form the basic kinematics equations, which we use to predict motion. Each of these equations has their angular version as well, which is a one-to-one substitution with their linear counterpart. After completing kinematics, we began a study of dynamics. We began this by starting with Newton's laws, first being the law of inertia, which we represent as mass and as a resistance to acceleration. The rotational counterpart is moment of inertia, which for the first time is a function of the shape of the object as well as its mass. Next, we began the discussion of force with the introduction of Newton's second law. Force's rotational equivalent is torque and is symbolized by the Greek letter tau. We will begin our discussion of torque with a review of Newton's second law. With a little bit of algebra, it can be stated as the sum of the forces is equal to and in the direction of the acceleration times the mass. Using our substitution techniques, we can come up with an expression for torque. Instead of force, we substitute torque. Mass is replaced with moment of inertia, and linear acceleration is replaced with angular acceleration. This is Newton's second law in rotational form. Taking a closer look at just one torque, instead of the summation of all of them, and in magnitude only, can be expressed this way. Let's begin with a little substitution. Instead of moment of inertia, let's replace it for its most generic expression, which is mr squared. Separating the r's, the expression looks like this. With a little bit of regrouping, we can isolate r times alpha, which you may notice as linear acceleration. Again, rearranging our variables and grouping m and a together, we notice that we have a force. This is what a torque is. It is a function of a lever arm and a force, or a distance from a pivot. Putting it back in its vector form yields the lever arm r cross product with the force vector. The cross product x is not a typo. It is a specific type of vector multiplication called a cross product, which means that the two vectors that are being multiplied need to be perpendicular to one another. Let's take a familiar object like a meter stick, with its center located in the middle of the object. This is the point we will use as our point of rotation, often referred to as the pivot or axis of rotation. A pivot is identified by the triangle underneath. Once a point of rotation has been established, it should be used as the origin for all future measurements and calculations. If we consistently use the Cartesian system, plus being to the right, positive up, negative left, and negative down, we will get consistent results and uniform interpretation. Let's begin by taking our lever arm and extending it along the body from the pivot. Then we will place the force perpendicular, as is the rule for torque. Notice that when I take a positive lever arm times a positive force, I get a positive torque. This positive torque produces a counterclockwise rotation and is the reason that all measurements of angles are positive and move in the counterclockwise direction from any axis. If we look at a force supplied to the other side of the pivot, we again extend along the object first, and then supply the force perpendicular at the end of the lever arm. In this scenario, we have a negative lever arm multiplied by a positive force, which will produce a negative torque. A negative torque therefore causes a clockwise rotation. In our final scenario, we move again along the object to the left of the axis, but this time the force is produced at an angle. Because torque is a vector product and requires the two components to be perpendicular to each other, we need to separate the force vector into its pieces that are parallel to the object and perpendicular to the object. Using trig, we find that the parallel portion is equal to f cosine theta, while the perpendicular portion is equal to f sine theta. The portion parallel causes translation, meaning motion left or right and up and down. Basically, everything we have talked about all year to this point has been translation. The part perpendicular produces rotation, which is the point that we want to focus on. Isolating just the portion perpendicular that we want to look at produces a torque that in magnitude is equal to the lever arm times f sine theta. Now, let's put this all together. Newton's second law in rotational form talks about the summation of torques. Looking at the three torques, our first torque that produced counterclockwise rotation, our second torque, which was negative and produces clockwise rotation, and our third torque, which again will produce clockwise rotation. If we put this all together by applying the second law, we start with a summation of the torques. In its vector form, it looks like this. But, like with forces, we like to take care of signs in the first step, and that way we don't have to worry about them again later during the substitution values. Applying what we've learned about clockwise and counterclockwise motion, we can write the statement as magnitudes with direction included. Substituting for each torque yields this expression, taking each one's lever arm times its specific force. The statement of second law, net torque equals I alpha, we take our original expression and instead of net torque, we replace it with I alpha. Because we used a meter stick, its moment of inertia is specifically 1/12 ml squared, where L is the length of the meter stick, or 1 meter in this case. Dividing by that moment of inertia, we get an expression for the acceleration as we did applying second law. The summation of the torques divided by its inertial characteristics, which in this case is rotational.